Let's start today's lesson with a quiz. This question asks you to identify any compounds of these four choices that will both undergo SN1 hydrolysis and also produce only a single product. So go ahead and pause the video and see if you can come up with the correct answer. So let's figure out what the answer is. SN1 hydrolysis involves the loss of the chloride to form a carbocation in the rate determining step. Three of these compounds can reasonably undergo SN1 hydrolysis. This compound down in the lower right will not undergo SN1 hydrolysis, at least not to an appreciable extent, because it will result in the formation of a vinylic cation. We try to avoid the formation of these vinylic cations where we have a carbocation showing up where there is also a pi bond. So when the criteria that we're looking for specifies that it has to undergo SN1 hydrolysis, it seems like that one would be out. The remaining three compounds now, they will all undergo SN1 hydrolysis, but let's see if they meet the second criteria. The second part of the question asks us to find compounds that will produce only a single product, and that gets to the issue of carbocation rearrangements in the form of an allylic rearrangement. So we'll go ahead and kind of evaluate all of these simultaneously. So the chloride's going to come off. Go ahead and pop that off of all of them, and it will be replaced by a carbocation. Let me clean this one up just a tad. And that carbocation will show here. Now, resonance tells us that each of these is going to undergo an alpha to gamma delocalization of that positive charge. And so this pi bond is going to hinge over to the other position, and that will shift the carbocation to that position right there. Okay? So after the chloride falls off to produce a carbocation, the carbocation is going to delocalize to either of these two positions. And then water is going to come in and capture that carbocation in the next step. The question doesn't ask me to show a mechanism. Hopefully this is a mechanism you're familiar with, but I'm going to cut some corners here and just skip right to the ultimate end product, and that's going to be an alcohol. And if you're not familiar with that particular mechanism, then you want to go back and review the Wheel of Doom. So these are the two products that will be formed because of allylic rearrangement during the SN1 hydrolysis. These are not the same. These are two different compounds. We can check that by naming them. Let me pop the name up on this one. So this is 1-methyl-cyclohex 2-ene-1-ol, and this one over here would be 3-methyl-cyclohex 2-ene-1-ol. So this compound is not going to meet the criteria that we've outlined, where it has to undergo SN1 hydrolysis, and it will do that, but it only produces one product, and in this case it produces two different products. So we'll evaluate the resonance structures that this compound could make. The carbocation can show up either at that tertiary position, or the pi system can hinge over and will move the carbocation to the secondary position. In the next step of the mechanism, when the water comes in and captures that carbocation, and then the last step where that water will get deprotonated, we're going to end up forming two different alcohols. Okay, this is a secondary alcohol with a tri-substituted alkene. This is a tertiary alcohol with a di-substituted alkene. This is a good example of a kinetic versus thermodynamic product, where this would be the kinetic product because it went through the tertiary carbocation, and this would be the thermodynamic product because it produced a tri-substituted alkene. But it's not the question, it's not the answer to the question we're asking, because we want something that will produce only a single product, and these are two different products. You could argue, well, what if you ran it under kinetic conditions? Would you then only get a single product? And the answer is, not really. You're going to still get a mixture of products, and that's not exactly what the question's asking. The other resonance structure of this compound right here, we can just produce that by flipping it horizontally. If I fold the pi system over to the right, that will jump the carbocation alpha to gamma, and when these two carbocations are attacked by water, which then gets deprotonated to form the alcohol, we end up producing the exact same compound. You can verify that with the name. So this is E3-pentene-2-ol, and also E3-pentene-2-ol. With that resonance delocalization of the pi system, you might end up with some product that's Z but the answer that the question, the guess what the question answer is we're looking for this one right here. This is what we're looking for as the answer to the question. You could make an argument that this would end up with a racemic mixture, so you'd also get more than two products here, and that's also true. This is just a messy question. Okay? So perhaps this isn't the best thought out question, but hopefully it illustrates the point of allylic rearrangements and how those can influence the type of products you get in a chemical reaction. This slide represents a review of elimination in chemistry, as well as some additional details that we encounter when we start using allylic systems. This is a normal secondary alkyl halide in the presence of a strong nucleophile that is also a strong base and is small. We expect it to undergo E2 chemistry following Zaitsev's rule to produce the trans-2-butene as our major product. When you have an allylic system like this, you have two options. One in black is the preferred option, but it appears to go anti-Zaitsev. One of the ways of stating Zaitsev's rule is that you pull the hydrogen from the carbon with the fewest number of hydrogens. That would be the red arrow pathway right here, because this carbon only has one hydrogen. This carbon has three hydrogens. But the other and probably better way of thinking about Zaitsev's rule is that you should pull a hydrogen so that you make the energetically more stable product. And that's what's happening with this black pathway right here. A conjugated diene is much more stable than a cumulated diene. So Zaitsev would tell you to make the conjugated diene. The energy diagram for all three, the blue, the black, and the red, is going to end up being a concerted mechanism with one hump. The blue arrows right here are going to cross that hump and then drop down to some new energy level. If we try to model the black molecule on kind of the same energy spectrum, what you should notice is that this reaction happens faster, meaning that hydroxide is more reactive as a base to the allylic position than to just a normal alkyl halide, because the product ends up being conjugated. If instead the hydroxide is trying to pull off this hydrogen to make the unstable cumulated alkene, then you're going to have a very large activation barrier and drop down perhaps not at all in energy. I don't know what the energy difference is for making a cumulated diene, and so it's going to just not be as favorable as making the conjugated system. The whole point of this slide is to help you understand that E2 chemistry is much easier on the allylic position because the molecule can release a lot more energy, it's more spontaneous, and it's more favorable to produce this conjugated system over here on the far right hand side. On the previous slide, we saw the formation of this 1,3-butadiene, which is about the simplest conjugated system that we encounter. Now we're going to ask, what can you do with 1,3-butadiene? And this represents the simplest electrophilic addition mechanism. The pi bond can reach out and pick up a hydrogen off of a halogenic acid. Instead of hydrogen here, I'm using the isotope deuterium. They react identically in a chemical fashion, but I want to keep track of where that hydrogen ends up, so the deuterium allows me to do that. The product of these arrows right here would represent this secondary carbocation with the deuterium out here on the end, and then in the second step of my mechanism, the halide ion would capture the carbocation, and we'd end up with our final product. I have an asterisk here to represent that this is now a chiral center. So this would be a racemic mixture, 50% S and 50% R. Anytime you start off without a chiral center in your starting material, and you introduce a chiral center, you're going to end up with a racemic mixture. The energy diagram for this reaction follows kind of this two-stage process, where the first step is the rate determining step because we're making a carbocation, and then in the second step, the halide ion captures that and we drop significantly downhill in energy so that it's overall a spontaneous process. Hopefully you can anticipate what's going to happen next, and that's allylic resonance. So in addition to the carbocation showing up at this secondary position, it will also hop via alpha to gamma allylic resonance, or you can think about the pi bond kind of hinges over, and it moves the carbocation over to a primary position. If the halide ion happens to capture that carbocation in the primary position, then we end up with a different product. Energetically speaking, this blue pathway is going to be identical until we get to this point right here. But when the carbocation is localized to this primary position, then the next step where the carbocation is captured by the halide ion will go through a higher activation state because you're forcing the carbocation onto a primary, less stable position, but your final product has a di-substituted alkene instead of a monosubstituted alkene, so you drop to a lower energy state overall. When you have a higher activation energy, which represents a slower reaction, but a lower overall thermodynamic endpoint, then you're going to cross your two lines, and this is where we start to run into that kinetic versus thermodynamic product. These products, in addition to being called kinetic and thermodynamic, which we'll get to in a second, are often also called 1,2 addition and 1,4 addition. And this is why I labeled the hydrogen as a deuterium, to help you see better that the 1,2 doesn't mean that we are on the 1 and the 2 position according to the correct rules of nomenclature. It just means that the halogen is on one position, and relative to that position, the other thing that I'm adding is the next position over. So that's what's called 1,2 addition. 1,4 addition is where the halogen ends up, or whatever new substance ends up on the 1 position, and the other substituent ends up at the 4 position relative to that. Generally speaking, 1,2 addition does typically correspond with the kinetic product. This is the kinetic product because the carbocation is at the more stable secondary position, and the 1,4 addition will often correspond to the thermodynamic product, and this thermodynamic product is the more stable product because of the di-substituted alkene. Unfortunately, there are exceptions, and so I don't like having students pair those concepts. There are cases where a 1,4 addition will lead to the kinetic, and a 1,2 addition will lead to the thermodynamic. This is not that case. This is the norm. But you don't need to memorize that 1,2 is kinetic and 1,4 is thermodynamic, because hopefully you can identify the kinetic product simply based on the stability of the carbocation intermediate, and the thermodynamic product should be identified based on the stability of the alkene. The mechanism for this reaction is the same, regardless of whether this pi bond is there or not. In other words, the conjugated alkene doesn't cause the chemistry to look different from a mechanistic perspective. Still, a pi bond reaches out, picks up the hydrogen, bumps off the halide, and in the second step, the halide ion captures the carbocation. That is not the case when we react a conjugated alkadiene with a molecular halogen. In this example, the correct mechanism shows the pi system reaching out to pick up a halogen, bumping off the second halide, and the distinct formation of a carbocation. If this pi bond were not present, then instead what we would see is the formation of the polonium ion intermediate. That polonium ion intermediate has all kinds of stability problems associated with the three-membered ring, but it's better than a carbocation, and that was true in the past. In this particular example, though, the carbocation is actually better than the polonium because the carbocation can undergo allylic rearrangement. So this resonance delocalization from the alpha to the gamma position, that is called allylic rearrangement, represents a more stable case than the formation of this polonium ion intermediate. So the conjugated system has a different mechanism than an isolated system or a single alkene would. And the consequence of this different mechanism is that now we have that same kinetic versus thermodynamic issue. The halide ion can attack either the carbocation at the secondary position, or it can attack the allylic rearrangement carbocation at the primary position. We end up with the 1,2 addition product with that chiral center, or a 1,4 addition product right here. A 1,2 is typically your kinetic product, but we don't want to get stuck in that trap because even though your book likes to use that, it's just not that consistent. If you want to know if something is the kinetic product, look at the carbocation. This carbocation shows up at the secondary position, so this is my kinetic product. The alkene dictates the final product, a di-substituted alkene versus a monosubstituted alkene. tells me that this di-substituted alkene would be the final product, that is the thermodynamic product. Energetically, we see the black arrows representing the kinetic product, where the pi system reaches out to form the carbocation, and then the halide captures the carbocation in the second step. The blue pathway is going to show, and I did copy and paste this from the previous slide because it's the same deal, where when you move that carbocation over to the primary position, you end up going through a higher energy activation state. But because the final pi bond is di-substituted, you end up with a lower energy overall, and that's where we end up with the kinetic versus thermodynamic products. New topic, Diels-Alder reactions. These are very important chemical reactions that we see in both biochemistry and all over organic chemistry, and they're useful because they produce new carbon-carbon bonds. And those are usually hard to make, and when you can make them in a controlled fashion, it's a big deal. And so we're going to spend the rest of this lesson and the next lesson talking about the details of Diels-Alder chemistry. This represents the simplest possible Diels-Alder reaction. There is a simple alkene, and this is ethylene, reacts with 1,3-butadiene, and this pi bond hinges over to make a new sigma bond. So thermodynamically, that's a win. This pi bond hinges over to make a new pi bond. That's a draw. Like, there's no gain or loss thermodynamically. And this pi bond right here hinges over to make a new sigma bond. So really what I'm doing is trading 2 of these pi bonds for 2 new sigma bonds. And that represents an increase in stability, and therefore this reaction is energetically downhill overall. It's concerted. The energy diagram would be a simple one hump drop to a lower energy state, but this requires a lot of heat to get this reaction to work. There is an experiment that we run in the laboratory where we have students conduct the Diels-Alder reaction, and they actually have to take their test tube containing the 2 compounds that we're going to react in this Diels-Alder fashion over to a different general chemistry laboratory to put the compounds directly in the flame of a Bunsen burner to generate enough heat to get the reaction to run. We don't allow Bunsen burner flames in the organic chemistry laboratory because a lot of the vapors that we deal with are both flammable and heavier than air, so the fume hood has a hard time sucking them out of the room, and you can unknowingly, with a spark, set the air on fire in an organic chemistry laboratory. So it's an extreme fire hazard, and we've done pretty good about preventing that from happening in modern day chemistry laboratories, but it was a bigger deal back in the days of prevalent smoking in the laboratory. The Diels-Alder reaction can be thought of as a reaction between an electrophile and a nucleophile, and it would be great if we used those terms to be helpful to you, but we don't. And instead, we refer to the electrophile as a dienophile and the nucleophile as a diene. And hopefully that's not totally abstract. The diene is the thing with 2 pi bonds. That makes sense. And the dienophile is the thing that it reacts with. So perhaps that's helpful. But we need to be able to keep in mind that this concept of diene is also a nucleophile, and the dienophile is the electrophile most of the time. One of the reasons that a tremendous amount of heat is required for this reaction is because of the conformational requirements of the diene. The diene has to have both of the pi bonds rotated to the same side of the single bond. So I just took this molecule and copied and pasted it over here, and that arrow right here is trying to show you that this single bond is free to undergo rotation. And this diene can adopt what looks kind of like a cis arrangement or a trans arrangement. But these are not isomers of each other in the sense of stereoisomers like we typically see with cis and trans. They are simply different conformations of the same molecule. And so this S means that across the single bond it's cis, and across the trans bond it's cis. That's what the S stands for, is the single bond. And this molecule is free to undergo infinite rotation and flip back and forth between the S-cis and the S-trans. The problem is that the S-trans is the more favorable state. So while it can flip back and forth between the two, it spends an overwhelming majority of its time in the S-trans conformation, because this reduces the steric problems associated with the S-cis conformation. And so the heat is required to try to keep this thing moving constantly so that when it does bump into the dienophile, it can undergo the chemistry in that split second that you happen to catch this molecule momentarily in the S-cis conformation. That's why there's so much heat required for this reaction. It only works when the molecule adopts an unfavorable sterically discouraged conformational state. This particular Diels-Alder reaction is very difficult to accomplish in a laboratory because it has such a high activation energy barrier. And remember that this dienophile is an electrophile, meaning that it's supposed to accept electron density. So one of the ways to get the reaction to run a lot better in the laboratory is to use a dienophile. This is my dienophile right here that has an electron withdrawing group attached to it. And one of the standard features of the electron withdrawing groups is they typically have a carbonyl group associated with them. This is now a good electrophile because it is missing electron density. It's been pulled up by the oxygen, leaving a large buildup of positive charge. When we show the same three arrows, where this pi bond hinges out into that carbon, forcing this pi bond to hinge over here into this carbon, and that pi bond to hinge down, we end up with a product of this reaction. This is a standard Diels-Alder product. There are two potential products of this Diels-Alder reaction for this pair of reactants. The one that I showed you at first, where this is called an aldehyde, where the aldehyde electron withdrawing group ends up adjacent to the methyl group, or where the aldehyde ends up one carbon removed from where that methyl group shows up. And that would occur if the two molecules bumped into each other in a different orientation. So imagine that this compound right here was flipped vertically, which is what I did, and then we ran the Diels-Alder reaction. We could instead produce this product right here. These two potential products are constitutional isomers of each other, and one of them would most likely represent the compound that you're interested in synthesizing, and the other one would represent an unfortunate byproduct that you'd have to then remove as a kind of a contaminant. In order to understand how to be able to predict which product is the major product and which product is the minor product, I need to introduce you to some nomenclature rules that we apply to di-substituted benzene rings. A benzene ring is a six-membered carbon ring with alternating double bonds. So this right here is a benzene ring. Di-substituted means that I have two things coming off of that benzene ring that are not hydrogens. I'm showing you all the possible di-substituted benzene rings in a single picture, so what you need to see is that the R group represents one of the things coming off of my benzene ring, and the other thing coming off of my benzene ring is coming off either at the adjacent carbon, at one carbon removed, or across the benzene ring. So if the two substituents are on adjacent carbons, they are called ortho relative to each other. If they are straight across the benzene ring from each other, they're referred to as para, and if you have to hop a carbon in order to get to the other one, they're referred to as meta. So these two are ortho, these two would be meta, and these two would be para. When a Diels-Alder reaction can produce two different compounds, there is a high probability that the relationship between the things hanging off of this newly formed six-membered ring will be either ortho or para relative to each other. Now technically they're not called ortho because this is not a benzene ring, but if it were a benzene ring, then these two substituents, this aldehyde and this methyl group, would be ortho relative to each other, and this aldehyde and that methyl group would be meta relative to each other. And the ortho-para rule tells us that this is more likely to be our major product. We're not going to get into the why of this rule. We're just going to use it as a rule and then step away from the explanation. One more important note to think about with the Diels-Alder reaction is the stereochemical consequences of things hanging off of the dienophile. So for example, if I were to run this chemical reaction with a cis dienophile, where both of these R groups are on the same side of the alkene, then they would stay cis in my final product. They would end up on the same face of the ring. And if these two R groups were trans relative to each other when I started the Diels-Alder chemistry, then they would be trans to each other relative to this ring system. So the stereochemistry of the original alkene is preserved in the stereochemistry of my final product. There's one other feature of Diels-Alder chemistry that is unique, interesting, and probably a bit confusing, so I'll do my best to walk you through it. This right here represents a common starting material for Diels-Alder reactions. This is the dienophile, and this over here is the diene. This cyclopentadiene is actually a fairly reactive diene because it is permanently locked into an S-cis conformation by this fifth carbon in the ring right here. In magenta, what I've shown are the active ingredients of the Diels-Alder chemistry, so they're the only ones participating in the chemistry, and we end up producing this as our product. These over here are called esters, and there are two of them. These two esters are cis relative to each other in my starting material, and therefore they would be cis relative to each other in my final product. Let me back up and show you that transformation. So over in this product right here, I didn't bother to specify that these two esters are going to come off of either the same face of the ring system. So they're either both going to be down or they're both going to be up. And when that happens, when both of these esters, because they started cis, they will end cis, when they're both down or they're both up, I end up with two different options. While both options show these ester groups as cis, in this option right here, they end up kind of poking into the plane of the screen, and so does the pi bond that is formed during the Diels-Alder reaction. In this product over here, those two esters end up poking out of the plane of the screen, and they are on the opposite side of the screen as the pi bond. They have a special name for the relationship between the substituents hanging off of the dienophile and the new pi bond that is formed. If they end up being on the same face, so if both of them are pointing in, the substituents and the pi bond, then it's referred to as endo. If they're on opposite faces, then it's referred to as exo. Let me try to show that in a simpler diagram. So endo and exo refer to the relative position of the substituents of my dienophile and the pi bond that is the result of the Diels-Alder chemistry. So I'm asking about what is the relative orientation of this group right here, specifically focusing on that carbon and this pi bond. If they're both going into the plane of the screen or they both end up on the same side, then that's referred to as endo. If instead they end up on opposite sides, which is what's happening over here, that this carbon that used to be a substituent of my dienophile is poking out of the screen, but the pi bond is poking into the screen, then they're referred to as exo. If I take this six-membered ring right here and kind of turn it sideways, then that's what you're looking at right here. That's that same six-membered ring. This bridging carbon that's coming across the top is this bridge over the top. And hopefully now, maybe this gives you a better view of how endo means that the substituent coming off of that six-membered ring is down, and the pi bond is also down. They are endo because they're on the same side. If the substituent is up and the pi bond is down, then they are exo. For reasons we're not going to talk about, endo happens to be the preferred orientation when you run a Diels-Alder reaction where there are substituents coming off of your dienophile. Third topic of the day, and this has to do with molecular orbitals. Sometimes students are exposed to molecular orbitals in general chemistry, and sometimes they aren't, and usually they forget whether they were or they weren't. So I'm going to back up all the way to general chemistry and try to introduce the concept of molecular orbitals very quickly, and probably not very effectively. Molecular orbitals are based on the concept of the wave-particle duality of electrons. When two waves come together, you can think about these as two electrons or two photons of light or two sound waves. When they come together, if they are in phase, meaning that one wave is reaching its crescendo at the same point that the other wave is reaching its crescendo, then when you add those two waves together, you'll end up with what's called constructive interference. And you'll end up with a resulting wave that is the sum of the heights of the two waves that composed it. Destructive interference is where the waves come together perfectly out of phase, where one of them is coming up and is at a maximum, the other one is at a minimum. This diagram on the right-hand side is trying to show you how those waves would look like in water. You'll have to imagine that there are two probes that are sticking into the water that are vibrating very quickly to produce waves. So the probe here that's shaking and making waves, and you can see the waves kind of moving outward from that probe. There's also a probe over here that's making waves, and those waves are moving outward, and what you're looking at now is the intersection of those two waves. When those waves, water waves, run into each other, and the waves are both kind of at a maximum height, then that represents a dark spot. And the reason for that is there's a flashlight and a camera kind of where your eyes are, and you're sending photons in towards that tub of water, and then they're bouncing off the bottom of the tub and coming back to your eyeballs. If they have to pass through more total water molecules, fewer photons will make it back to your eyes, and that represents a dark spot. So the dark spots right here represent these peaks of constructive interference. The widest spots represent the troughs of constructive interference, where the water level is the lowest, so more photons are making it to your eyes, so it looks wider. And then somewhere in the middle of this, there is this destructive interference, where the water level stays the same, where the waves cancel each other out, and the water looks like it's unperturbed. By analogy, electrons in their orbitals will do something similar. Now I'm going to dumb this down a little bit, and so if you are an expert on frontier molecular orbital theory, you might have to cringe a bit, but hopefully this is a working definition of how molecular orbitals work. Imagine that you have two different hydrogen atoms. Now a hydrogen atom in the dark recesses of space or a vacuum all by itself will have a single electron, and that electron will reside in a 1s atomic orbital. When you bring that hydrogen atom adjacent to another hydrogen atom, those two hydrogen atoms will bond to each other. And we would show that as, in Lewis theory, as just two H's with a line between them. In molecular orbital theory, we need to recognize that when those electrons come together, they're either going to come together in phase, where the electrons produce constructive interference and build up kind of a pillow of electron density between the two nuclei. And that pillow of negative charge allows the two positively charged nuclei to draw close to each other. So this is the bonding orbital. But if they can come together in a bonding fashion, they will also come together in an anti-bonding fashion, and both of these new molecular orbitals will simultaneously exist in the same space. And the electrons either occupy this orbital, where there's room for two electrons, or the electrons will occupy what's called an anti-bonding orbital. In an anti-bonding orbital, the electron waves come together with destructive interference, and no electron density resides between the two nuclei. This is a nodal plane, and you end up with the two positively charged nuclei being repelled by each other, and the negatively charged electrons kind of fleeing away from that nodal plane, pulling the molecule apart. That's why this is referred to as an anti-bonding orbital. The things you need to take from this hydrogen molecular orbital diagram is, we take these atomic orbitals and we combine them together. For every atomic orbital you bring to the table, you have to produce a molecular orbital. So if I brought in two atomic orbitals, which I did right here, then I would need to produce two molecular orbitals. They typically come together in a bonding fashion, and they will come together in an anti-bonding fashion. The lowest energy bonding molecular orbital will have no nodes, and the next higher energy molecular orbital will have one more node. So if this has 0 nodes, then a step up in energy will produce 1 node right there. We have acronyms for these orbitals, so I took the same figure that I made right here, and I just cut out this part, and I'm just focusing now on my new molecular orbitals. These are orbitals that they belong now to the molecule, and the molecule will choose to either park electrons in them or not until all the electrons have a home. Well, since molecular hydrogen only has 2 electrons, both of those electrons are going to go into this bonding orbital. And energetically, the bonding molecular orbital is going to be a lower energy state than the anti-bonding molecular orbital. So this is a diagram that represents the exact same thing as the previous diagram. It's just trying to show it in a different representation. Sigma 1s means that this is a bonding orbital between 1s orbitals. Sigma star 1s means that it's an anti-bonding orbital between 1s orbitals. Both of the electrons will occupy this lower energy orbital, and this is referred to as the highest energy occupied molecular orbital. It's occupied, and it's higher in energy than any other occupied molecular orbital in the system. It just so happens that in this system there is only one molecular orbital. So you could probably just call it the occupied molecular orbital, and this molecular orbital is the unoccupied molecular orbital. So this happens to be the lowest energy unoccupied molecular orbital. That's why they call it a LUMO and the HOMO. The HOMO is the highest energy occupied molecular orbital, and the LUMO is the lowest energy unoccupied molecular orbital. When we start looking at more complicated systems, then we have to think about only the electrons that we absolutely have to. This is referred to as frontier molecular orbital theory. It's the idea that if there are orbitals that are not doing any chemistry, let's ignore them. And in a Diels-Alder reaction, 1,3-butadiene is only doing chemistry with its pi electrons. And these pi electrons exist exclusively in p orbitals. So I am redrawing this 1,3-butadiene, that's what these 3 lines right here, as just its p orbitals. I'm just ignoring all the sigma bonds and just focusing on these p orbitals right here. Usually for simplicity's sake, they just redraw, leaving the carbon atoms out and just drawing these p orbitals next to each other right here. Now, hopefully you've seen these p orbitals before, and in the past there was a color difference typically, where they changed color when you went through the nucleus. That actually is a little bit of detail that we've ignored in the past, and that detail is that the phase of the electrons changes when we go through the nucleus. So if they are in phase in one way on top, they will flip to the exact opposite phase here on bottom. And by phase, what I'm referring to is how the waves are propagating. So if the waves are of one phase on top of a p orbital, they will be in the opposite phase on the bottom of the p orbital. And this system right here is a conjugated system where electrons can move freely across the top because all of these orbitals are in phase with each other, and they can move freely across the bottom because those orbitals are in phase with each other as well. What I have shown you, though, is only one of the molecular orbitals that are produced by this 4p orbital system. Each one of these p orbitals right here represents a separate atomic orbital. And when I move those atomic orbitals together in this fashion, they produce a single molecular orbital that could be diagrammed something like this, where the electrons can exist either above the carbon strand or they can exist below the carbon strand, and that represents a single molecular orbital. That particular molecular orbital is very low energy because there are no nodes. In other words, the electrons have no point where they are out of phase. If you move across the top, they're all in phase, and if you move across the bottom, they're all in phase as well. The next highest energy molecular orbital that we would get from combining these 4 systems would involve us adding a node to the system. So this, if we go up in energy right here, we can produce another molecular orbital, and we have to. If we started off with 4 atomic orbitals, ultimately we need to end up producing 4 molecular orbitals. and each one of these is a single molecular orbital. This represents another molecular orbital, but it is a higher energy molecular orbital because while there is good interaction across this gap, because the orbitals are in phase, they have a node right here where they are now out of phase. So every time we step up in energy, we add another node. So the next highest energy right here would have two nodes, and if we move from left to right, now these are out of phase, these are in phase, and these are out of phase. So going back down to the bottom again, there are three different in-phase interactions. The first, that's 1, and then 2, and then 3. That's best case scenario, 3 in-phase interactions. In the second one, there are 2 in-phase interactions and 1 out-of-phase interaction. So if you think about in-phase as being a good thing, we'll call that a +1, and out-of-phase being a bad thing, we'll call that a -1, and we add up what's going on. We have 3 different good interactions, so this would be +1, +1, +1. And we kind of refer to this as an overall quality score of +3. In this orbital, moving from left to right, I have an in-phase interaction, and I'll score that as +1, as a good thing. There's another in-phase interaction over here, I'll score that as a +1. But there's an out-of-phase interaction over here, which is anti-bonding and -1. So the sum is +1, +1, -1. This is a +1 overall. It's still a bonding orbital, but just barely. Like there's one more good interaction than there is bad interactions. In the next highest energy, where I add in 2 nodal planes, there's now a -1, and a +1, and a -1. To give us an overall score of -1 total, meaning that this is an anti-bonding orbital. I don't have any more electrons to put into this orbital right here, so it is empty. And the reason that I have 4 electrons, if you remember, my original system is 1,3-butadiene. There are 2 electrons here and 2 electrons right here. They are found in 4 different atomic orbitals. So when I start making the molecular orbitals, this is the best case scenario, and I park 2 of those 4 electrons in here. This is still a bonding orbital because there are more bonding interactions than anti-bonding interactions. I'll park 2 more electrons in there. But now this anti-bonding orbital, I don't have to put any electrons in there because there are no more electrons in the molecule. To see if you have any clue what's going on right now, and I know this is a very complicated subject, and in my memory, I know explaining this in the past, I am staring at a sea of blank expressions of students. But try to pause the video and see if you can draw the next highest energy orbital. Let's see how you did. There would be 1 node in this one, 2 nodes here, and now 3 nodes. The overall bonding score here would be a -3 because every time I cross from one p orbital to another, I experience an anti-bonding interaction. So this would be worst case scenario, very unlikely to park electrons at all in this system. Because this represents the highest energy orbital that is occupied, so highest energy occupied molecular orbital, this is the HOMO. This is not the HOMO because while it is occupied, it's not the highest energy. In fact, it's the lowest energy occupied molecular orbital, and if we had a term for it, we'd probably call it the LOMO, which nobody says because nobody cares. The HOMO is the one that does all the chemistry, and it does it by interacting with LUMOs. So HOMO-LUMO interactions are a common expression that organic chemists use when trying to describe chemistry. The LUMO right here is the lowest energy unoccupied molecular orbital. It's unoccupied, it's the lowest energy, that's why it's called the LUMO. If you had to come up with a name for this, it would be the highest energy unoccupied molecular orbital, or the HUMO, which I've never heard anybody say. It's always the HOMO and the LUMO that we focus on in terms of chemistry. The goal of this portion of the lesson was to help you see how we come up with this molecular orbital diagram for 1,3-butadiene. On the homework, your job is to come up with a simpler molecular orbital diagram of just ethylene, as well as do some of the other homework questions. But the chalkboard problem is going to ask you to come up with a reaction, with a diagram for ethylene. Good luck with that. We'll pick up with this on the next lesson and hopefully fill in some of the gaps of your understanding and answer some questions that you are likely to have.